last session of the day, which is about alternative applications for CST technology. With alternative, we mean non-electrostatic CST plants. Actually, I would say that we've been talking about this topic all day long today, because we've seen so many applications for salination, for enhanced oil recovery, for chilling, for heating, and well, this is what I wanted to talk to you about. So everything is said, we can go. There are still a few topics, just one that probably has never been covered before. So I will focus completely in this presentation on that topic. But since a part of this presentation was dealing with polygeneration, multi-generation, which means using the solar heat to produce at the same time power, chilling, heating, and so on. And we visited a very relevant facility today, which is devoted to all of these applications. And we discussed about the STS-MED project, whose logo you have on your notebooks there. So we will continue, rather than me talking about polygeneration, we will show a video and that will be commented by the coordinator of the STS-MED project. And I think this is the best way of talking about polygeneration. As a conclusion, on a whole day, I would say, discussing this topic, rather than having a static lecture, we dealt this topic in a much more dynamic and I think also fruitful way. So I would like to ask
the video is still there. Unfortunately, I have to go upstairs for a meeting in less than 10 minutes, so I can start the video, and might be that then Alaric can comment it.
Yeah.
I hope it was in the desk.
Is there any way of sending the sound to the speakers?
Yes.
I think the only way is this.
No. This morning, just stop it.
It's difficult.
Yeah, it's a point. It's a tricky point there.
It's the tricky IBM pointer. But I think the video also. Yeah.
Yeah, I also I have the idea for you, so okay, perfect.
We are in the middle of one of the STS-MED demo plants. This is the plant in Palermo. It's a large field that has been installed inside the university campus in an area that the university has given for the project. This is the end of a long project. One of the STS-MED demo plants. This is the plant in Palermo. It's It's a large field that has been installed inside the University of Palermo campus in an area that the university has given for the project. This is the end of a long project that lasted for 4 years, where we have analyzed the behavior of high insulated regions in the Mediterranean area. We have 14 partners, all distributed in the solar belt in the Mediterranean Sea. These are demonstrative plants that want to show that we can use the solar energy with polygenerative approach to give services to buildings, to settlements, and to communities. We have designed plants with the right mix of technologies to link solar collectors with high performance with a system that can generate the different services to be provided to the buildings.
This is the first time that in Sicily we create a solar laboratory available for all the researchers of the university and for the technicians that want to understand the use of solar system. We have installed here 3 linear Fresnel collectors, mirrors able to heat an oil and the thermic oil inside the absorber tubes. We heat the oil till about 250 degrees and we store all this energy inside thermal storage. We designed the first thermocline molten salt thermal storage of about 400 thermal kilowatt hour, able to give this energy to an ORC, an equipment that we use to produce electricity, and a chiller. This kind of systems is a polygenerative system. And it's very important for the community, for the scientific community and for technical community to understand how these systems can be replaced in all Euro-Mediterranean countries.
The system that we have installed in Cyprus, in about a year, providing cool air to the adjacent building. Cyprus has peculiar needs for energy, especially in the summer. Concentrated solar power is an alternative to the well-developed photovoltaics that we have all around the south, the Mediterranean and all across Europe and the world, or an alternative to the wind power that we also have in the island at the moment. Scientifically, the project is very interesting. We have finished commissioning it and we expect to do a lot more experiments with it in the next 2, 3, 5, 10 years. So there is certainly an element of sustainability for the project and for the system itself.
A camera permits us to have a real-time view on the field of Cyprus. This solar platform will reduce dramatically the energy consumption from air conditioning of this near to zero energy building. In Cyprus, many roofs like the one we see on the video, on the camera, are located in the city. They are flat and the orientation is optimal for the settlement of a Fresnel collector.
I am now at the rooftop of Al-Khwarizmi building at Al-Hosn University College. The CST plant behind me is a major deliverable of STS-MID project. The specific objectives of the project are to facilitate the adoption of CST small-scale integrated systems in the Mediterranean basin and to create new opportunities for the commercial and industrial sectors by improving technical skills of professionals and enabling SMEs to set up a full supply chain in the solar energy sector. The plant generates electric power, cooling, heating, hot water, and distilled water from a single source of energy, which is solar energy.
All the plants share the idea to be multi-generation plants. That means generating electricity desalination, water heating and cooling to fit the requirements of the buildings. Especially, these plants are connected via a central control system in which all the partners can view and monitor the performance of other plants in other countries. It is not only for plants, it is for schools, it's for research schools, it's for teaching schools installed in 4 different countries, and by itself it is sustainable. For example, in Egypt, we have got the training of simple technicians. For the first time they installed such plants. We have got experience now. We have local supply chains, local manufacturers who were interested and who were involved in the installation of such a plant. Thank you for ARCA, thank you for MB, thank you for ASRT, thank you for all the partners from Jordan, Italy, Cyprus for their efforts in this project. Thank you.
So this gave the final overview of the polygeneration approach. What we can do with the solar heat collected. I think this is very comprehensive, even if it's for a relatively low temperature plant in this case. But you can get many different functions. So, let's see what else we can do with solar thermal energy then. Now we're focusing on exploring heat, not electricity, or at least not only electricity. So all the applications we can do either in parallel or exclusively, and I think it's schematically shown in this slide. We can use the plungers to produce heat and use this heat in any process that requires heat without having to produce also electricity. So this is CST technology. Then we can have the solar field dedicated to process heat. We build the solar field just to produce heat and use heat. But we can also, as we have seen on Monday, use the solar heat to power a thermal power station, to produce electricity, and then use the rejected heat from this plant. We discussed this morning when talking about power cycles. You know that we need to reject some heat from the plant in order to complete the power cycle. And in that case, that heat can still have a sufficient level of temperature to be useful in other processes. And a typical example is desalination, which will be the object of the second part of next week. However, when you follow this approach, which means that you use rejected heat from the thermal power station, you have two competing requirements. Because under the point of view of the power station, you want to keep the quality of this heat, then the temperature level of this heat as low as possible, because this means higher thermal to electricity conversion efficiencies. On the other hand, if you lower the quality of this heat, you won't be able to use it, so you will be just rejecting it to the environment. Sometimes, like in the case of desalination, you can find a trade-off. So you can lower a little bit the efficiency of the power plant by increasing the temperature of steam condensation, and use this heat for some applications like desalination. And finally, another configuration that I will show you in some application we will see later is that, okay, I'm not taking waste heat from the power plant, I'm just devoting a part of the solar field to producing heat and a part of the solar field to producing power. And possibly I can also feed both this energy into the same process, as we'll see later. And basically, what you have seen today in the STS-MED approach is this, because in the general scheme of the STS-MED project, all the heat collected by the solar field goes to the storage, and then the different utilities, users, take the thermal energy from the storage. So they are all at the same level and exploiting the thermal energy coming from the solar field. They're not after the power block. So they are in parallel with the power block. Okay, this is the general concept. What can we do then with this heat? And by following the different approaches that we have mentioned. Okay, we mentioned these applications many times in the last days, I would say. We mentioned desalination, solar heating and cooling, and solar cooling also is one of those rare, fortunate occasions in which the production capacity is naturally matched with the demand. Because when we have much sun to power our solar field, we also need more cooling. So it's a very good way of combining, of using the concentrated solar power. Also small parabolic troughs, not the one you've been talking about at this moment. The one with like almost 8 meters of column aperture size. Then we have the textile industry, washing, bleaching, dyeing again, and we have a contained level of temperature for the heat required. The chemical industry, mostly, you have different kind of application. Like the chemical industry is mostly about producing a process or service stream for the plant. You have usually 3 levels of pressure, which correspond to 3 levels of temperature. We go from low pressure steam, below 140 Celsius degrees, we do temperature steam among 140 to 105, and high pressure stream about 205. Then hot water and cooling, and finally also solar fuels. And you see that in this case the temperatures are much higher, because as we will see later, here we are using high quality energy, high quality heat to produce a valuable chemical which has a high energy content. So this is, I have a slide about each of these technologies, but I'm not going to discuss them because we already talked about this morning. Arik also mentioned this application, and you're going to have 2 whole days about desalination. So we can save time on we don't talk about desalination. The only point is that there is a good potential for coupling and using the waste heat, but this requires, first of all, increasing the discharge temperature of the steam from the turbine, then lowering the efficiency of the power cycle, and then also building the plant close to the seaside, where usually the DNI is not always optimal. So there are some competing factors that must be considered. However, you're going to discuss this in detail next week, so let's skip. Again, we will be very quick about advanced oil recovery. It's rather recent application because it's been discussed also this morning. So in this case, you use solar generated steam to do enhanced oil recovery. You may know if you're familiar with the oil industry in general, but especially with heavy oils are in the reservoir are porous rocks, and in order to obtain the so-called flow assurance of the hydrocarbons contained in the reservoir, you need specific characteristics of the pressure of the reservoir, of the viscosity of the fluids, in order to ensure a correct outflow out of the wells. This is why usually, and this becomes harder and harder as the reservoir becomes depleted, because you are taking the resources from the reservoir. In that case, because the pressure of the reservoir gets lower, and this is why also when you produce oil, you're producing also water together with oil. And what is done in the oil industry, you separate water from oil, you treat the water, and you inject back the water in the reservoir to enhance the extraction of further oil. In this case, it's not only a problem of, say, pressure to bring the oil out, it's also a problem of viscosity of the heavy oils contained inside the porous rocks. So the injection of steam inside the injection wells ensures a better flow and the possibility of exploiting also more difficult fields. This is a rather recent application. Under the CST point of view, it is interesting not only because we find different and diversified fields of application, but because there is this interesting technology designed by Glass Point, which is a new design trough contained in glass houses, which are specifically designed to protect the mirrors from sand and from getting soiled, because in the desert environment, of course, it is a big issue. There is a cleaning system embedded in the glass houses.
Also, it's needed clean after that. I think it's also needed clean.
Yeah.
Need to be clean.
Yeah, there is an embedded cleaning system for the glass houses, which is part of the design. And also, they are not exposed to strong winds, so this allows to have a very light structure, and they have a very peculiar trapping mechanisms in which the trough are rotating around the axis of the focus of the trough. So this is very particular compared to the design that you have seen and we were talking about up to this moment. Yes.
Excuse me, what about like the greenhouse from outside? There is no dust.
Yeah, the cleaning system is from the outside. So it's, I don't know the details about the works, but they claim that they have an embedded cleaning system that keeps the glass house clean.
But like the power trough, like to mitigate against the sand and washing every time, they're putting the cover. Or is it?
No, sorry, I didn't get it.
They built it like the cover around the power trough to mitigate the dust deposit.
Yeah, on the mirrors. But of course,
Outside is.
you have to clean the glass house, and the glass house is equipped with a cleaning system, not for the parabolic trough, but for the glass house itself.
It's easy.
It's easier than cleaning the mirrors of the, and especially the glass house is not moving. So here, by protecting the mirrors from the wind, you can use a lighter structure from the wind for the collectors. This is another advantage.
Is there any loss from the cover?
Reflection.
Reflection and
they don't give all the details, of course, this is a commercial project. So we must rely on the information they're providing. And of course, when you get information from the people who are selling the technology, you must be very careful, okay? But they claim very interesting prices. They did a significant pilot test. They already tested a 7 megawatt pilot plant. I would say it's more than a pilot plant session. And they're going to build, announced building 1 gigawatt. Then probably this testing was successful, but I don't have the details about the performance.
I guess, first it's tracking inside, right?
Yeah.
Yeah, but I guess glazing of the mirror itself must be simpler, no?
Yeah, the whole mirror assembly is much simpler and lighter.
The glass cover of the mirror itself, maybe it's really thin.
Thin. The whole structure is very thin because it's rotating around the collector.
When receivers, and we need here several millimeters of glass, but maybe we even less here.
That's the main point. Not only protecting from dust, but also from wind and to allow a lighter and simpler structure. And I mean, the costs are very interesting. Then another, it's nice to see picture, to see ships enjoying the shade of a Fresnel collector. This is a dairy industry in Sardinia. And in this case, this is used to produce steam for the dairy industry. So this is a good example of integration with the existing existing environment. But there's not much to say
It's
here.
barbecue.
Yeah. When it's lunchtime, you send some sheep to on the farmer's line. It's very good. Okay. And now let's go to solar fuels, because this is something that you heard of for the first time in this course. I don't know if I think some of you is working in this field. I heard you're working there. But I think I'm not going to talk about the processes you're working on, because I know what it's been studying.
So mainly with water and CO2 splitting.
Okay.
Using syngas and other fuels.
I think you're working also on steam reforming?
Yeah.
Okay, we're talking about steam reforming, but hopefully under a new perspective, because when talking about solar reforming, usually you talk about high temperature reforming like the usual process. In this case, I decided to talk about another approach to steam reforming. So when we say solar fuel, we say hydrogen in the first place. Even if solar fuel is not only hydrogen. But I would say it's the first solar fuel, the first component that has been studied as a solar fuel, and basically starting from hydrogen you can make all other solar fuels by reacting with CO2, as I was mentioning, by using processes which produce, we can say they produce hydrogen as an intermediate, and then they finally produce methane. However, here you see that the properties of hydrogen, and we're not going to go into the details, you know that it's the lightest, even those of you who are not chemical engineers or chemists know that hydrogen is the lightest. Probably don't know it's the most abundant element in the universe, but it's not very important for the solar fuel point of view. It's the lightest, which has some advantages and many drawbacks in handling hydrogen, because being so small, hydrogen can rather easily permeate and we have leakages. So besides that, it has a very low critical temperature. You see, -24,340, which means that it's also not very easy to store. Because either you compress very much the hydrogen, also because since it's so light, in order to store a significant amount of hydrogen, you need to have very high pressures. And also because if you want to store significant amounts, you can go to the liquid phase, which is the usual approach with other components, but in this case, to go to the liquid phase, you definitely need cryogenic transport. You need to go to a very low temperature. On the other hand, the heating value is interesting, and we will see it possesses other very interesting properties. What we do with hydrogen today, we don't use hydrogen as a fuel, not really. There is something starting, but we've been talking about this now for decades, but presently the use of today's use of hydrogen is mainly as a chemical product, chemical feedstock for the industry, for the chemical industry, for the hot food industry to do the treatment of the fat treating, and for mineral processing industry, it's used to reduce ores that are extracted from mines, and you can get metals out of it by reaction with hydrogen, which has a strong reducent. And these are definitely non-energy related uses. The chemical industry is mainly the industry of fertilizers. And indirectly energy-related use are used in the petrochemical industries, in the downstream processes of the oil and gas industry, which means it is used to prepare the gasoline, for instance, to change the properties of the hydrocarbon mixtures used for the gasoline, to improve their properties, to remove sulfur by a hydrotreating system, and so on. So here you have an idea of what is the application of hydrogen today. Roughly 50% of production is for the production of ammonia. Then we're still in the fertilizer industry, and then it's used in the oil refinery for 37%. And then this is what I'm talking about when I say petrochemical industry. Methanol production, which is another very important feedstock for the chemical industry. From methanol you can produce a lot of other chemicals. And other industrial uses, and also a small, but not so small considering the market of the aerospace application. You know, the hydrogen can be used also as a rocket fuel, and there's several applications in that spacecraft for producing electricity and also for producing water where it is difficult to store. How do we produce the hydrogen we need for all these purposes that we have listed? At this moment, we're producing hydrogen out of fossil fuels, mostly methane, but not only. 48% of the production is out of methane, natural gas, then from oil, carbon. You see, either way, it's a fossil fuel. We do it through so-called reforming processes, which basically extract the carbon atoms from the hydrocarbons, and they leave only the hydro, and they take away the carbon. And more than 95% of the production is from steam reforming. And steam reforming trains a big production of CO2, because CO2 is steam reforming processes are strongly endothermic, which means that we have to provide heat to these processes, and it's really high temperature heat. We're talking about 700, 900 Celsius degrees to have a significant yield of hydrogen. And then how do we provide this heat? By burning fossil fuel. That's what we do best. And not only, one of the products of the steam reforming is CO2. So we have CO2 as a product of the reaction. We have CO2 produced because we need heat to carry out the reaction. So this is why you get from 10 to 12 tons of CO2 for each ton of hydrogen you produce. And this is roughly each year, the world production is about 60 million tons of hydrogen, which, if we compare this, which is hydrogen needed for chemical uses, with the hydrogen would be needed to cover the world energy requirement, this is like 2%. So if hydrogen becomes a significant energy carrier, the market is completely different. We have this problem, CO2 emissions in hydrogen production, which, as we will see, can be significantly addressed by if hydrogen is produced using renewable energy sources and not by burning and converting fossil fuels. Here you have a map with the hydrogen production sites in Europe. You see that it's rather diffused. They are usually production is carried out within ammonia plants and within refineries where it's used in large quantities. Okay, now let's move to not to the chemical use of hydrogen, but to the energy use of hydrogen, which is more the topic of today's lecture. So this is the methane combustion. You all know, I think. Methane combustion is the way we get energy thermal energy from methane by making it react with oxygen and producing CO2 that's now seems like the worst enemy of humankind. Probably we also have other bad enemies, but now CO2 is getting much attention. So we can get energy also by oxidizing hydrogen with water. This is the hydrogen combustion. But you see a very important difference. In this case, you don't have the production of CO2 if you burn hydrogen. So this is one of the first interesting aspects of hydrogen as an energy carrier fluid, rather than what we use now, which is hydrocarbons. So what are the positive aspects of using hydrogen as an energy carrier? First of all, we have just seen that hydrogen, which is misspelled here, does not produce CO2 when burned. When not oxidized, I would like to say, because burning hydrogen is something that I don't like very much, and I'm going to explain better what I mean. Then, if hydrogen is produced by using renewable energy sources, probably we are removing the CO2 problem. Why? If we produce hydrogen from water, and I will show you, this means reversing this reaction here. We get water and we produce hydrogen and oxygen. Then we start with a non-carbonaceous feedstock. We end up with a fuel which, when it's used, does not produce CO2. And if we, of course, we have to provide energy, a lot of energy, I tell you. And if this energy is provided without the production of CO2, then we get a completely carbon-free fuel. It is free of carbon when I produce it. Is it free of carbon when I use it? If I start from water. Yes?
We were converting CH4 into CO2. CH4 is quite causing harm from the environment. Is it CO2 this harmful for the environment?
CO2? CO2 is not toxic, it's inert, but you know there is a big environmental concern about CO2 emissions, which are now widely recognized as the cause of climate changes, and this is why there's a big pressure of reducing the CO2 emissions worldwide.
CH4 as well, I think.
Sorry?
CH4 is causing that global issue as well.
Definitely, and it's much stronger greenhouse effect than CO2, of course. But if we, I don't know, what do you mean exactly? We're not.
Well, I mean, it's using the best hydrogen production method. It reduces the harm of CH4 in the environment. So it would be a green method.
But I mean, that's CH. We don't spill methane in the environment. So in that case, the way you produce hydrogen is that by using a valuable resource. So it's not the same problem. CO2 is a waste that usually it's really hard to contain. It's really hard to separate from the effluent gases of our plants. While of course you may have losses on CH4, but it's something that you contain. Usually you get CH4 from the gas wells. I mean, you have leakages, but it's not something that you're just throwing away in the environment like we are doing with CO2 right now. Okay.
I remember that in Promes, in France,
yes,
they were cracking methane with the solar energy.
Yes.
They were extracting hydrogen and having solid carbon.
Yes, this is another one of the several processes.
And then the carbon you can use it for industry. I mean, no, it's what do you think?
Depends on the quality of carbon. There are now it's not so easy, however, to separate the.
They were going like 1,400 degrees. That's what I remember. They were using in the big
because but you don't need actually to do cracking such high temperature. Okay. There are more recent processes that allow to produce to do cracking also at lower temperatures. However, this is another of the processes that now is gaining again interest, and however there are some issues in separating the quality and type of carbon that you're producing and how to separate it from the reaction mixture. But aside from this, this is another very interesting development.
It's not pure carbon that you get, you mean?
Yeah, it's pure carbon, but carbon you may have different qualities because now people are trying to get a valuable form of carbon out of these processes because you know that you can have graphite, which has a very high value, and there are processes that are aimed at producing also this type of carbon.
So you mean that you can bypass the solar energy? It's not mandatory to use the solar energy to crack methane.
You can do also with fossil energy, but of course we want the interesting point is providing clean heat, solar heat to do this type of processes. In any case, cracking, okay, it's a different class of processes, but the idea is the same. You take the fossil fuel, or not only the fossil fuel, the carbonaceous fuel, because we will see you can also have biomethane, for instance, produced by anaerobic digestion. and you take away the carbonic part, either as CO2 in the reforming, either as solid carbon in the cracking.
How efficient can be the process to get hydrogen from water?
This is the object of what comes after. So, hopefully your question will be satisfied. Okay, so if we produce it from water, this is our main aim. We want to produce it from water because this is really clean. However, we will see that probably now we're very good. We do it from carbonaceous feedstock, and at least if this carbonaceous feedstock is renewable, like biogas or like bioethanol or something like this, then at least we obtain a renewable fuel. It is still a carbonaceous fuel. Sorry, it still comes from a carbonaceous fuel, and then we will have to deal with CO2 production while we produce hydrogen. But this CO2 is much easier to capture in a centralized station rather than having to capture when you burn the fuel in a decentralized way. And finally, you can produce it from fossil feedstocks like it's done today, but you replace the fossil energy input with a renewable energy input like solar heat. And also in this case you have some advantages, but because you have a fuel upgrading, which is obtained with solar energy, then you're feeding clean energy into your fuel, you're increasing the energy value of your fuel, and this delta energy that you put in is clean. So you are increasing the cleanliness of the fuel you have, and in any case you have an easier CO2 capture. Not only that, I told before I don't like to say burning hydrogen, because using hydrogen as a fuel in a flame, to burn in a flame, produce energy in a thermal way, is really a waste of this valuable fuel, because hydrogen can be made react with oxygen. Then you make this reaction, but not thermally, not just mixing hydrogen and oxygen together and igniting this mixture and having a flame and heat liberated, but you can do it electrochemically in a fuel cell. So in this case, you have a device in which the same reaction is carried out, but you have the direct conversion of chemical energy into electrical energy. What is the difference in burning hydrogen and then using this heat to produce electricity? But if you burn hydrogen, you have heat, then you go through a thermal electric conversion processes like those we have seen this morning. And then at that point, the second principle of thermodynamics will want installed. You have to pay to convert. You cannot convert 100% heat into electricity, because the second principle of thermodynamics tells us that not energy is conserved, but not all types of energy have the same value. It's like buying a car that it's worth, I don't know, 10,000 euros, or having 10,000 euros. Okay, the car is worth 10,000 euros, but nobody's going to give me 10,000 euros for that car if I pay 10,000 euros. While with the same amount of money I can do whatever I want. So it's the same with electricity and heat. I can convert completely electricity into heat, I cannot do the opposite. So this is why this type of conversion is much more efficient. Hydrogen can be an energy carrier. There are several scenarios that have been considered, in which, for instance, countries that enjoy a very high ENEA, very high insulation, can produce hydrogen with solar processes, and then, but they also have a small population. They can export this clean fuel to countries that have strong emission control policies. A typical example is Australia, which exports a lot of energy to Japan, and of course, exporting directly electric energy is not possible. There is no cable that goes from Australia to Japan, so finding a way of exporting energy it's always a good way of exploiting the resources. Australia is a net exporter, it produces much more electricity than it consumes. So this is a possible scenario. Even if I must say that transporting hydrogen is not that simple, but there is a lot of studies on producing so-called hydrogen carriers, transforming hydrogen in something that is more transportable than transforming back to hydrogen when it arrives at the destination. Okay, this is, I mean, we would need 1 week to talk about this, so let's move forward. Okay, I told you before that hydrogen, we were talking only about hydrogen, not only about also other solar fuels, because out of hydrogen you can make all other fuels. You can start from carbonaceous feedstocks and or water, as we will see, and by adding energy, you can get hydrogen. Either you use hydrogen directly as a fuel, for instance, this is an automotive application in a hydrogen car, which is an electric car, which features a fuel cell and uses hydrogen in an electrochemical way, with an electrical motor. It's not burning hydrogen, but it turns it into electricity. Either we use hydrogen, of course the automotive application is just one example, it's not only for cars, it's for using energy, also for stationary applications. Or by combining hydrogen with CO2, and this is very interesting because once in a while we find a process that consumes CO2 instead of producing CO2, we can produce also conventional fuels, methane, also gasoline, then gaseous and liquid fuels, or also chemicals. Now, I hope you're now interested in knowing how we can produce hydrogen from solar energy, especially from concentrated solar energy. There are several classes of processes. Here we have the thermal input, the concentration of thermal input, high temperature heat. You can find mainly two classes here of processes. One class which has as an input a carbonaceous feedstock, which can be a fossil or biofuel, natural gas, biogas, oil, coal, and bioethanol, and so on. Or another class of processes, this here, which don't use a carbonaceous feedstock, but use only water as input. Okay? As we will see, this is much closer to what we do today, so it's easier and it's closer in the future, the possibility of just replacing the energy input from fossil energy to renewable energy. So this is, I would say, the mid-term option, and then this is probably the final objective, producing water using renewable energy. You can do this with so-called purely thermochemical processes. Thermochemical, you convert thermal energy into chemical energy. And this is very interesting because we convert a noble form of energy into a noble form of energy. Or we can use some noble energy in this process. And then you can have the so-called hybrid processes, which combine electricity and heat. Of course, there are also purely electrochemical processes which use only power, but this is not interesting for us who are not doing with PV, but we're doing with CST. Okay? As for the processes that start from fossil or from carbonaceous feedstock, we will see an example of solar reforming, which is the reforming of methane, which means producing hydrogen as we are doing today, but replacing the energy input type, moving from a fossil type to a renewable one. And in this case, I will show you also an example of a hybrid process, which uses water as an input and both thermal and electric input. Okay, let's start with the process which is closer to what we do today. So how we produce today hydrogen mainly by this reaction here. This steam methane reforming. So we get methane, we make it react with water vapor of course, and we produce hydrogen and CO2. This is the result of several other reactions that are occurring in parallel. The point is that the process is strongly endothermic, takes a lot of energy, and it occurs at a very high temperature. In the conventional process, which is the most deployed today, you carry out this reaction. You must boil the water, you must produce the steam, of course, which is very energy consuming. You must heat up the methane. Steam and methane must be heated up to, it's not heated up to slightly less than this temperature here. And it's fed to reactors, which are tubes filled with a catalyst. The gas passes to the catalyst that is converted. These tubes are immersed in a furnace and you provide the energy. Of course, you provide the energy with a fired furnace, which means you're producing CO2. You're producing CO2 here, you're producing CO2 because you're providing heat. The pressure is between 10 and 40 bars, and the temperature is, as you see, is very high. Usually it requires 2 reactors because you have a first step at high temperature, this temperature in which you carry out this reactor, and you produce the so-called syngas, a mixture of CO, carbon monoxide, and hydrogen. And then, since your objective is obtaining hydrogen, you want to further convert CO into hydrogen, you carry out the Golden-Gas-Shift reaction. And then the sum of these 2 reactions, the overall result is this reaction here. So you have one high temperature reactor followed by one low temperature reactor. And the main approach in the solar fuel community now is to carry out solar reforming exactly in the same condition as in the conventional process. The only difference is that we don't want to burn a fuel to provide the amount of heat. We want to use high temperature heat because we have to go to this temperature. This temperature means that can we use a Fresnel system to attain this temperature? No. Can we use a parabolic trough? Not even. Today, even if there is some study to prove it, we must use a point focusing system, typical of solar tower, because the dish wouldn't have the necessary capacity to have a convenient process. So either we do it directly, putting the reactor on the focus of the focal point of the sensor receiver. Either on we have some intermediate heat exchange fluid, basically air. However, what is the problem? As I told you this morning, probably you don't remember because I had to be so fast this morning, and I don't know if you got everything that I said. At this temperature level, today we don't have any mature heat storage techniques, which means that we're not able to stabilize. Yes, we have some short-term buffering possibilities, but we cannot think of extending the working hours of our chemical plant. So this is going to be very tough to carry. This is the main challenge in the high temperature steam reforming. Because what happens if you have a very cloudy day, what you do, you have to shut up the plant each night for sure, or use backup fuel, then in the end you're producing hydrogen exactly as you're doing right now by burning fossil fuels, so there are several processes. So what I'm presenting you today is a project that's been coordinated by ENEA and it was concluded last year. It's called Cometry, in which the main challenge was to develop so-called low temperature steam reforming process. So instead to try to adapt the heat storage and solar system to be able to operate this process at 700, 900 Celsius degrees, we wanted to change the conditions and make it convenient also at lower temperature. And in a temperature range where we can use the consolidated heat storage approach in the CSP industry today, which means double tank molten salt. This is perfect. 550 Celsius degrees, 450, you can use solar heat and you can benefit from the commercial solution from storage. So you can ensure a smooth and continuous operation of the plant. So what are the advantages of lowering the temperature? Some of these are trivial. You can use lower grade materials, of course. You have a higher safety of the plant. And this is more chemical. You don't need one high temperature, one low temperature reactor, because you carry out in the same reactor the steam reforming, this reaction, and this reaction in the same reactor, just one step. You save one piece of equipment. And then, under our point of view for this school, the most important one, advantage, you can use solar power from CST using molten salt as heat transfer fluid. What are the advantages? Then you can produce hydrogen up to 100% from renewables if your carbonaceous feedstock is a renewable, like biogas. Or in any case, you can reduce CO2 emissions and you can facilitate very much CO2 capture with this process, in any case. What are the problems? Why don't we do usually steam reforming this temperature? Is that this is a strongly endothermic reaction, which means that it wants to operate at high temperature. Otherwise, it is an equilibrium reaction, which means that if the temperature is too low, when these two components that are feeding to the reactor start to react and form the produce will start to react back and form the reactants. Then you will have a very low yield. Even if you have a huge reactor, you can, whatever effort you can make, you will convert like 10%, 15% of the methane you're feeding. So your process is not convenient. Another problem of operating at lower temperature is low reaction kinetics. So you must have catalysts that can operate at low temperature. And then you must have low catalyst that you can have low catalyst rotation, but I don't think we have the time to get into the details of this aspect. So all these drawbacks were investigated and addressed within the project, especially the one dealing with low hydrogen yield. I don't know what is your chemical background, but basically when you have a chemical equilibrium reaction, the temperature and pressure in the tube rate tells you, given one starting point, how much you can go to the other side. Okay? But this happens, the reaction will apparently stop because at a given point the product will start to react back and form the reactants, the products. So, but if you continuously withdraw one of the products from the mixture, this point, this equilibrium will never reached. So if we manage to remove hydrogen as it is produced within the reactor, the temperature won't be a problem under the thermodynamic point of view. I will push the reaction, it will continue. Because if I remove hydrogen, it won't be available to react with CO2 and produce again the reactant. So what has been used in this process is a membrane reactor. There is a membrane embedded in the reactor, the reaction space, which extracts hydrogen from the reaction space. And this allows to push the conversion. Then also active catalysts were developed and also the catalyst carriers. This is the plant concept. You know this part by now you should know very well. Parabolic trough plant using in this case molten salt as a transfer fluid. Storage between 550 and 290 Celsius degrees. Of course, we're ENEA, we developed this technology, so we're focusing on finding ways of exploiting this technology. But of course, it doesn't make any difference if you replace the solar field with a solar tower operating with molten salt as heat transfer fluid. And then here you have the chemical plant. This is what's inside the chemical plant. The chemical plant must preheat, must boil the water, steam generator, must preheat. The mixture of methane and water must be fed to the reactor, and then must provide the heat required by the reaction within the reactor. So all these steps here can be heated by using solar heat, which is provided in a smooth way by exploiting the storage system, which acts not only as a way of extending the operating hours of the plant, but also as a way of smoothing the operation during the day, also when you have fluctuating conditions due to clouds and so on. This is very good because the chemical plants don't like to operate discontinuously or in a fluctuating mode. In this case, the membrane is separated from the reactor in this schema. In the reality, they are integrated, and I will show you how in the next slide. Then you have another very good point is that you get pure hydrogen downstream of the membrane. So you get pure hydrogen. Usually, after the reactor, in the industrial reactor, you need separation steps to recover pure hydrogen. In this case, you're already recovering a pure stream of hydrogen. Then you have some residual hydrogen in the effluent together with carbon dioxide. But in this case, carbon dioxide is highly concentrated. And highly concentrated means also it's much easier to capture compared to other conditions. Okay, here there are the development of all the components of the reactor, starting from the catalyst to the membrane for hydrogen permeation. But I just want to focus on the reactor because I think it's an interesting equipment also for those of you who are not chemical engineers or not interested in chemical processes. Because basically it's a shell and tube heat exchanger. So this shows that we can use, just like we build steam generators to be fed with hot molten salt to produce steam, we can design heat exchanger and use this hot stream of molten salt in any process we want. So this is another way of using process heat taken from the concentrated sorbent. Each tube, I think you're all familiar with the shell and tube heat exchanger. So the molten salt flow on the shell side, while the reaction occurs within the tubes. The tubes are actually an inner tube, and it's a tube assembly, an outer tube, and an inner tube, which is a hydrogen permeable membrane. You see it here. So the catalyst space, you see it's an annular space around this inner tube, which is the membrane. Membrane allows the passage only of hydrogen. All other components are retained that can cross the membrane. And finally, we go to the a pilot has been built with a reactor and tested in a simulated molten loop circuit, and the conversion, the results were very interesting. Here you see now another very big challenge when you want to use process heat from the CSP plants, or CST plants. It's how to integrate the chemical plant and the CST plant. So in this case, you see that you have a solar field here. Several configurations were studied. Here you see a configuration in which the co-production of hydrogen and power is envisaged. So your solar field is partially used to power the reforming step and also to produce steam to produce power. So you have co-production of hydrogen and power, and this can definitely increase the competitiveness of this type of processes, because of course now the cost of these processes is still high compared to the conventional processes, not only because of maturity, but also because the cost of the solar energy technology is being discussed. Now let's move to the other class of process. Of course, I'm just giving you two examples because the list of processes that can be considered for solar hydrogen production is rather big. Rather than having 20 slides focusing on each single process, I preferred to study with a more bigger detail two examples of the two main classes. One from carbonaceous feedstocks, another one from water. So let's talk about hydrogen production from water, which we said should be our final objective. This is called water splitting. You split one molecule of water or two molecules of water into two molecules of hydrogen and one of oxygen. This requires energy, as we said. This is possible through purely electrochemical processes. like electrolysis. This is a rather old, under the scientific point of view, process. However, today, for the industrial massive production of hydrogen, it's not very significant because it uses big amounts of a very valuable energy. So if I have electricity, I prefer to use it for other uses and produce hydrogen with cheap thermal energy obtained by fossil fuels. However, this subject, the development of new, more efficient electrolyzers is a very active research topic now because direct electrolysis at ambient temperature, or close to ambient, up to 100 Celsius degrees more or less, like the alkaline electrolysis process, is very interesting now that we have, as we have said this morning, excess electricity production in the grid in some moment of the day. So this is being studied as a way of storing the excess electric energy produced by the non-dispatchable renewable energy technologies like wind and PV. Then, if we want to use a less valuable energy input, we can move to thermochemical and hybrid processes. This direct splitting of water into hydrogen and oxygen can also be done with purely thermal input. But in this case, the second principle tells I want a very valuable energy type. So either you give it as electricity, either you give it as high temperature heat. But in this case, the temperature is definitely too high. So there are studies of doing the direct thermal splitting of water using very high temperature solar heat. But the problems are immense because, first of all, you have to deal with materials that can withstand these temperatures. Then you're producing hydrogen and oxygen in the same step. Then you have an explosive mixture which is ready to explode as soon as it finds any sparks or anything in the air. So my opinion is that it's not very interesting to pursue this way. Other processes, purely thermochemical cycles, and we will see what is a thermochemical cycles right away, and then hybrid cycles, which include high temperature electrolysis, hybrid processes. So what is a thermochemical cycle? We said if we want to go just by giving a thermal input from water to hydrogen and oxygen, this requires very high temperature. But if I can find some other way around this single step, straight step, there is a way of giving, of course, the same amount of energy, probably something more because when you increase the path, you have more losses, but dealing with lower and possibly more acceptable temperatures. This is the idea behind the thermochemical processes. So, what are the advantages? Thermochemical processes are a cycle of chemical reactions that occur in cycle, in which there are components which are continuously produced and then consumed, and the only net effect is splitting water into hydrogen and oxygen. But with some advantages. First of all, hydrogen and oxygen are produced in separate steps, so you don't have the problem of explosive mixture. They require significant thermal input, but there are processes that rely only on purely thermal input without any electricity. Some cycles can operate also below 1000 Celsius degrees, which is high, but it's reasonable for the perspective of the temperature that can be attained with the central tower systems. And therefore, these processes are in general suitable for coupling with the CST plant. If you look at the literature from the 70s, you find pages and pages of thermochemical cycles that in principle could work. Sets of reactions that can carry out with these conditions could be used. However, despite this long list, I think it's more than 100 cycles that have been proposed, only few today appear as reasonably feasible at industrial level. Furthermore, most of these cycles were initially conceived to be powered with nuclear heat. You may know that the fourth generation of nuclear reactors, the so-called very high temperature reactor, it's a type of reactor that has a big amount of rejected heat, just like the power plant we talked about. The difference is that the rejected heat from the conventional power plant is at 40 Celsius degrees. The rejected heat from fourth generation reactors is 1000 Celsius degrees. So it's not really a waste. It's a very, very valuable source of energy. So it was thought, let's use this high temperature heat to produce hydrogen. So all these processes were conceived to use this energy input. We want to replace the nuclear heat, nuclear byproduct, which is heat, in this case, with solar heat. The problem is that nuclear heat is continuous. You have it 24 hours a day, you don't have fluctuation problems. When you want to replace it with solar heat, and then it's a challenge, because solar heat is fluctuating. So it's not so easy to adapt processes that were conceived to get a continuous energy input with a fluctuating energy input. In this, here you see one example of the numerous cycles that were proposed. It's a cycle of the so-called sulfur family cycle, which is based on two steps. One step which occurs at low temperature, below 100 Celsius degrees in general, and one step which occurs at high temperature, at least more than 850 Celsius degrees. In the low temperature step we produce hydrogen, in the high temperature step we produce oxygen. The high temperature step is thermochemical, we need high temperature heat. The low temperature part, there are processes of this family who use thermal input, other who use an electric input, like the one I'm talking here. The hybrid sulfur is called hybrid because it uses electricity. Okay, here there should be a thunderbolt going here to say that this step in the hybrid sulfur process is carried out with electricity, while the high temperature step is carried out with heat. Here you find the reaction. You see that basically, you see water reacts with sulfur dioxide and another molecule of water. So you have two molecules of water, one of sulfur dioxide. You produce hydrogen, which is the product, and sulfuric acid. Then sulfuric acid can be decomposed into sulfur dioxide and water, and then you can further decompose SO3 into SO2 and oxygen, and you remove oxygen. And then the cycle starts back again. So there are lots of reactions, but the net product is the production of hydrogen and oxygen. And this can be powered with solar energy. This is the key point. There is another project which is ending in 2 weeks, which was about studying and facing the challenges of adapting this cycle. Was originally conceived to be powered with continuous nuclear heat and to replace it with solar heat. You may see here a guy you should know by now. This is the DLR ULIF tower, which was used to test a pilot reactor to carry out the high temperature step with solar heat. While in Finland, an electrolyzer which carries out the low temperature step was developed. So the key components were developed and the process was analyzed. I will just here, this is the process block diagram. We don't not go into details. I just want you to show you that the input required is 42% electricity and the remaining is heat. High temperature heat, 23%, and medium temperature heat. What I mean with medium temperature heat, I mean heat below 550 Celsius degrees, which can be provided with a molten salt storage system. So this is the concept of the plant. This is the chemical plant. We're not going into the details. We just see that the chemical plant has several energy inputs. You have electricity, the blue arrows that are getting inside the plant. The orange arrows, which is medium temperature heat, 550 Celsius degrees maximum, and the red arrow, which means high temperature heat, above up to 1000 Celsius degrees. So, according to what we have set up to today, we can provide this medium temperature heat by using a parabolic shaft system, which can also rely on storage. For the high temperature step, we don't have a choice, we must go for a point focusing system. And unfortunately, we said we don't have a consolidated storage technology here to ensure the same extension, the same duration storage. So in this case, no storage was considered. As for the electricity, we can rely either on the grid, either on the electricity produced by a power block using the same molten salt. So you see, this is a possible integration between the two different types of solar plants and a chemical plant. The only problem is that, in this case, this part of the plant, which is fed with storage, can work continuously, while this part of the plant, which relies on the high temperature heat input, must work discontinuously. So this is the biggest challenge in integrating the solar plant with the hydrogen production plant. And in this case we have the red part is discontinuous. It works only when we have enough solar resource, while the green part here works also continuously because it can rely on the storage. Of course, to allow for this mismatch into the operating regimes of the two parts, we must have storage tanks in between. So we store sulfur dioxide and sulfuric acid, but this is also a way of storing energy. Basically, this is a chemical storage, because when we have sun to power the high temperature part, we do the cracking of the sulfuric acid and we store liquid CO2, which is a feedstock for the second part of the process. So we have we're turning what is a limitation, a drawback, into an opportunity, because this plant has several opportunities of flexibility during the year. We don't have time to discuss this, but as you can see here, I have also the possibility of having SO2 entering the plant and also of selling sulfuric acid. So depending on what is the solar resource, I could switch the production from hydrogen to sulfuric acid, which is a commodity, there's a market. Not only, I can do sulfuric acid by buying SO2. SO2 very often is something that people want to get rid of. They remove it from their gases, then they have to sell it sometimes at very, very cheap prices. Okay, this is about opening the cycle and also having a co-production of sulfuric acid and hydrogen, but there's no time. There is no time also to talk about high temperature electrolysis. It's not a big deal because we have seen two processes representative of two ways of producing hydrogen out of solar energy. How do we assess the efficiency of these processes? Usually, very often, too often I would say, people just calculate the efficiency of these processes as the lower heating value or higher heating value. It's more, you can decide which you prefer, provided that you declare which type of heating value you are considering, of the hydrogen produced divided by the total energy input that you put in your process. Of course, this is not fair here. This brute and energetic efficiency is not a good metric, because we're doing all this stuff because we want to use not electricity, but we want to use heat, and we want to use solar heat. So if electricity and heat have the same value, then do electrolysis at ambient temperature, because it's easier, it's just one component, you don't need all this thing. The point is that heat does not value as electricity. So we need a metric that allows to quantify this different value of electricity and heat. So either you use an exergetic approach in assessing the efficiency, either you use the so-called thermochemical conversion efficiency. So we consider what is the equivalent heat entering the process. So this is the energy value of the hydrogen produced, okay? As the energy input, we take the heat as it is, okay? And when we have electric input, we must convert it and account for a thermoelectric conversion coefficient, which is less than 1, of course, to state, wait, electricity is worth more than heat, okay? In this case, you can see that these processes are competitive with more simple electrochemical processes occurring at ambient temperature and ambient pressure, because they make use of a less valuable energy source. One last word on the cost of all this stuff. How much does it cost? Of course, as everything that you have seen, we're not today competitive with the conventional ways of producing hydrogen. Hydrogen produced with steam reforming is strongly dependent on the price of gas, of course, of the fossil fuels. And you may say it's around €1 per kilogram, more or less. Depends on the value, the cost of natural gas mainly. So these are the targets set by the fuel cell and hydrogen joint undertaking, which is an organism within the European Commission which manages the financing projects in this area, hydrogen production. And these are the targets set by FCHEU. Today the cost, the state-of-the-art cost of hydrogen production by water, from water by high temperature cycles, just like the one we have seen, the last one, it's 12 euros per kilogram. But the target for 2025 is 5 euros per kilogram. And today we should be around 10. And I can tell you the techno-economic analysis carried out of the project that you have seen here now is a price of between 8 and 11, it depends on the location you build the plant and also on other variables. For a very small production capacity, which is 2.6 tons per day, it's a small capacity. This was a constraint that we had in the project, but this means that if you build a bigger plant, you can get even lower prices. But as you can see, we are in line with the trend, so we can expect to achieve this type of target. And as for the other process, which is sun-powered, but is more conventional approach, we're very close to being competitive with the conventional production line. So I hope this was not too tough for you, because I know it was very technical and it comes at the end of the day when you're tired. I hope it was interesting in any case, and if you have any question, of course, please go ahead.
Luca, maybe I missed some information from the first part of the presentation.
Yes.
I was not here, unfortunately. Have you stated any minimum size for this kind of plants? I mean, there is a evaluation of the scalability of the process and the threshold to be effective on the economical point of view.
As for did you see both approaches? So from water and from methanol. The one from methanol, the name of the project is probably you know because the coordinator was Alberto. It's commonly where CO stands for compact. Compact, multi-fuel,
yes, I know that there is
so that technology is suitable to be built in very small scales. The problem is that if you want to power it with solar energy, probably the limiting part is the solar field.
Okay, so there is no limitation by the chemical side, the limitation is...
Yeah, of course, the economies of scales are important, but under a technological point of view, it is scalable and very modular because it's a shell and tube configuration which is very modular by design. As for the other technology, that is definitely not scalable because we are still thinking about a solar tower and parabolic trough field. So this means a big size. But we may consider in the future a small tower system with small parabolic trough, but we must check the temperature levels which are required.
Just leave it
And I think that already the size that we were asked to consider, which is 2.6 tons per day, it's a very small size.
Yeah.
And those prices we get could be much lower if we go higher. Any other questions? So if there are no other questions, I would like to say goodbye because I'm leaving tomorrow. So unfortunately.